In this video, we'll talk about properties and graphs of quadratic function. Let's recall that a quadratic function is any function that can be written in the form ax squared plus bx plus c, with the real number coefficients a, b, c, and the assumption that a is different than 0 to make sure that the function is indeed quadratic, right? This is a standard form, or sometimes referred to as general form, of a parabola. Let's observe properties of the graph of the basic parabola function, just x squared. To see the shape of this function, let's develop a few points using a table of values. If x is -2, x squared becomes 4. -1 squared becomes 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4 again. So we have the symmetry here and there that suggests that this point, the central one, is our vertex. So the vertex has coordinates 0, 0, it's here, and then to plot this pair of points, we'll go one across to the right and one up, and one across to the left and one up. Now the next pair, -2 or 2 with the value 4, we'll plot by going 2 across to the right and 4 up, and 2 across to the left and 4 up. So those are the 5 points that it's good to remember, and now we'll connect them to see the shape of the basic parabola x squared. So what are the properties of this graph? Well, firstly, the shape of it is a parabola. We observe that the shape has arms up, so it opens up. The domain of the parabola is all real numbers, because if we project those points onto the x-axis, entire number line will be shadowed by the graph. As a matter of range, now if we project our graph onto the y-axis, the graph will shadow any point from 0 to infinity on the y-axis. So the range is from 0 with 0, 0 can be taken, right, till infinity. And the vertex of this graph is 0, 0. As a matter of axis of symmetry, that's this line. This is the y-axis. So the equation of this line is x equals 0. Just for clarity, we use the usual scale, where 1 square represents 1 unit. Now let's observe how those properties change when we modify the function to, for example, x squared plus 1. Again, let's help ourselves with the table of values. We can check the same x values 0, 1, -1, 2, and -2. So when we square the -2, we get 4, but then plus 1, it's 5. Now, -1 squared becomes 1 plus 1, that's 2. 0 squared is 0 plus 1, it gives us 1. 1 squared is 1 plus 1 is 2 again. And we can predict that for 2 the value will be 5. Check it on your own. So let's plot those points. We'll start with the middle one, which is our vertex, right? So 0, 1, that's this point. Now, 1 across either way from 0, the value is 2. So 1 across and the value is 2 here and there. Or we can think that way, starting from the vertex. We can go 1 across both ways and 1 up. And then 2 across, and how many up? Well, we'll land on 5. So it's 4 up, right? And the same to the left. 2 across and 4 up. Those are the main 5 points that shape our parabola. Let's join them. Here it is. Observe how the graph of our function relates to the graph of the basic parabola x squared, that, as we recall, looks like this. Could we obtain the blue shape by translating the graph of x squared? Yes, it would be enough to move the basic graph one step up. Every point of the basic parabola is moved one step up. Even this one, 2, 4, it was here, now it is there. And this one, and that one. Okay, so could we graph this function without the table of values? Yes, we could. As long as we remember the shape of x squared, which is this basic parabola, it's enough to move the whole shape just one step up. It goes like this. Here we go. Let's observe the second function. Again, we start with x squared, but then we subtract 2. Can you predict where the shape of basic parabola will be moved? Yes, it will be moved 2 steps down. But to double check, let's still use our table of values to confirm. Okay, negative 2 when squared becomes 4, but then we subtract 2, so the value is 2. Negative 1 squares 1 minus 2, that gives us negative 1. 0 minus 2 is negative 2. 1 square minus 2 is negative 1 again, and 2 square minus 2 is 2. Let's plot those points. Again, we see that this is our vertex. How do we know it? Oh, just because the y-coordinate of it acts like a center for the other values that are distributed symmetrically around it. Okay, so let's graph our vertex 0, negative 2. That's this point. And then 1 across, 1 up. We land exactly at the point 1, negative 1, this one. And another 1 across, 1 up, that gives us negative 1, negative 1. And the last pair, 2, 2, that's this point, and negative 2, 2, could be obtained by starting from the vertex and going 2 steps across and 4 steps up, both ways, to the right and to the left. Okay, let's join those points. Here we go. Again, how this shape refers to the basic parabola, which goes like this. Well, the basic parabola was moved 2 steps down, exactly 2 steps down every single point, right? Let's see the movement. That's how it goes. As usual, we're going to use 1 square to represent 1 unit. So that's a point 2. This is negative 2. Here we have 1, and here we have 2. What we can observe on the base of these two examples is that if we start with a function that is well known, to graph a function that is modified by adding or subtracting certain number outside of this function, then the basic graph will be moved vertically by the number of units that we add or subtract. Notice that this vertical translation goes in the same direction as the sign indicates. If we add a number, the graph goes up, and if we subtract, it goes down. Now, how do the properties of these graphs differ from properties of the basic parabola graph? What has changed? Well, the main change was the vertical displacement. It caused the change of the position of the vertex. The vertex in the first example has coordinates 0, 1, and in the second example 0, negative 2. So the second coordinate of those new vertices are exactly those numbers that we added at the end of the function. What else has changed? Well, since the vertex moved to different spot, the range interval has also changed. In the first example, our range is from 1 to infinity. In the second example, it is from negative 2 to infinity. Again, this has something to do with the second coordinate of the vertex. Okay, let's see some other examples. What will happen if we modify our basic parabola function by adding 1 inside the bracket, adding it directly to the input x? Again, to check how this graph may look like, let's use a table of values. But this time, we want to choose x values that are around negative 1. Why? Because normally, if we work just with x squared, the central point is around 0. But this time, the central point 0 actually refers to everything what's in the bracket. So if x plus 1 is 0, that really means that x is negative 1. Therefore, this x negative 1 will act as a center of our inputs. Okay, so if we start with negative 1, let's choose couple numbers below negative 1 and couple above negative 1. So if x is negative 3 plus 1, that's negative 2. When we square it, we end up with 4. If x is negative 2 plus 1, that's negative 1. Square it, that gives us 1. Negative 1 plus 1 is 0. After squaring is still 0. 0 plus 1 is 1. 1 squared is still 1. And 1 plus 1 is 2. When we square it, it's 4. So yes, that's a confirmation, you see. This point will serve as a vertex for our parabola, because the other values are distributed symmetrically around this 0, right? Okay, so let's plot those points. -1, 0, it's here. Then 0 or -2 results in 1. So 1 across both ways, 1 step up. Here we go. And then 2 across from -1, the value becomes 4. 2 across both ways, the value is 4. Here we go. And we can connect those points. Here's our parabola. So how this parabola can be obtained directly from the graph of the basic parabola, which went like this. As you see, it's enough to move the basic graph one step to the left. All those important points one step to the left, right? Okay, let's see the movement. Here we go. Let's look at the second example. This time we subtract 2 from x. Again, let's use some table of values, but what kind of x values should we take? Similarly as before, think about the central point, which normally would be 0 for the input under the square. However, this time our input is called x minus 2, so the central point would actually be 2. Therefore, we choose 2 as a center and a few points before 2 and a few after 2 to have a good representation of points that will shape our parabola. Okay, let's develop the values. If x is 0, we have -2 squared, which gives us 4. If x is 1, 1 minus 2 is -1. When squared, it's 1. If x is 2, 2 minus 2 is 0, so after squaring it's still 0. 3 minus 2 is 1, square, it becomes 1 again. And finally 4 minus 2 is 2 square, gives us 4 as well. So we really ended up with the same values just because we chose nice axes. And again, this will be our vertex, right? That's a center, and here we have values distributed symmetrically around the center. Let's plot them. 2, 0, oh, that's here. Okay, then one step across to the right or to the left, we move one step up here and there. 2 steps across from the vertex, the value becomes 4. So 4 here and 2 steps across, 4 there. As you see, every single time we have this pattern. As soon as we figure out where's the vertex, we go 1 across, 1 up, 2 across, 4 up. Let's join those points. Here's our parabola. Again, how can we graph this function without referring to the table of values? If we start from the graph of the basic parabola x squared, it's enough to move it 2 steps to the right. Every single important point is moved 2 places to the right. Let's see the movement. Here it is. Okay, so let's observe the properties of these modified parabolas. How do they differ from the properties of the basic graph? Well, let's notice that the vertex in this case has coordinates -1, 0, and in that case 2, 0. We can observe that the first coordinates of our vertices are exactly opposite to the numbers in the bracket, aren't they? Remember on the previous slide when we added or subtracted something outside of the function, the second coordinate of the vertex was changed, and it was exactly the number that we added or subtracted. Now here, we add or subtract something inside the function just by the x. And this modification results in changing the first coordinate of the vertex into exactly opposite number. The second coordinate is still 0. Okay, what other properties have changed? We still have the same domain, we still have the same range, but we can observe the change in the position of the axis of symmetry. In this case, axis of symmetry has equation x equals -1, the first coordinate of the vertex, and in that case, the axis of symmetry has equation x equals 2. Okay, let's see some other modifications. This time, we multiplied our basic parabola x squared, in this case by 2, and in the next case by -1/2. So how this multiplication by 2 will influence the graph of the basic parabola x squared? Well, that's kind of easy to predict. Whatever the value we had for x squared, now it will be twice as large. So all the values will be stretched along the y-axis. But let's check it. If x is -2, when we square it, it becomes 4. But times 2 gives us 8. -1 squared gives us 1 times 2 is 2. 0 squared is still 0 times 2 is still 0. But 1 squared times 2 gives us 2. And 2 squared 4 times 2 is 8 again. So here's our vertex. Let's plot it. It's the origin. And then 1 across both ways, 2 up. Remember, it was always 1 across 1 up, but this time is 1 across 2 up. This is because of this factor of 2 in front of x squared. 2 across from 0, we have 8 up. So we have to approximate 8 because this is 5 and we don't have a grid, but that will be approximately 6, 7, 8, somewhere here. Similarly, for -2, the value sits somewhere here. Okay, therefore our graph looks like it's a bit thinner, it's narrower. Let's connect those points. Here's our graph. And how the basic parabola looked like? That's what it was. So the vertex didn't move, but our modified parabola is narrower than the original one. Okay, let's see the last example. Again, we'll use a table of values. -2 when squared, normally it's 4, but then we multiply by -1/2. -1/2 times 4 is -2. If x is -1, when squared, it becomes 1 times -1/2 gives us -1/2. 0 times anything is still 0. 1 will result in -1/2 again. Just because when we square 1 or -1, the value is exactly the same. Similarly with 2, it gives us the same value as for -2, so it's -2. And we can plot those points starting with the vertex at 0, 0. So 0, 0 is here, that's our vertex. And then 1 across both ways. The value at those points is -1/2, so it's here. And then 2 across from 0, the values are -2, so over there. Okay, here we go, and that's -2. Therefore, it looks like our shape is wider, and also it is flipped. It is not going with arms up, but with arms down. Let's connect those points. Here's our shape. And now, as you remember, the graph of the basic parabola looks like this. So the first thing that we need to do is to flip the shape over the x-axis. That becomes y equals -x squared. And then to obtain our modified parabola, we multiply every single value of the -x squared parabola by 1/2. So that was -4, half of it is -2, right? While here, we multiplied every regular value by 2. For example, this was 1, now it's 2. That was 4, now it's 8. Okay? So that's what multiplying by a certain number does to a graph. If we multiply by a number whose absolute value is less than 1, then the graph is wider. If we multiply by a number whose absolute value is more than 1, then the graph is narrower. Also, if we multiply by a negative number, the regular graph is flipped over the x-axis to the other side. So what kind of property changes can we observe here? Well, in the example when we multiply by 2, all the properties are actually the same. We didn't change the vertex, we didn't change domain, neither the range. Even the axis of symmetry is the same. The arms are still up. The only thing that did change is the shape. Our parabola is narrower. So the shape is of the form 2x squared. However, in the second example, we have some changes. The arms are positioned down. Therefore, even though the vertex is at the same place, we have different range. The range this time is from -infinity till 0. Other properties, such as domain or axis of symmetry, remain the same. except that the graph is wider. Now we may want to put together these two changes, add or subtract something just by x, and add or subtract something outside of the function. There's one more change. We have a minus in front of this bracket square. This minus causes that the whole graph will be flipped upside down, so the arms of parabola are expected to be down. Let's see the graph by filling up the table of values. Even though the choice of x's is really up to us, let's choose x values around the value that will make this bracket 0. So the bracket is 0 when x is equal to 2. Therefore, it's a good idea to choose some values before 2, 2, and after 2. Okay, if x is 0, f of x is negative 2 squared plus 1. So how much is that? This is negative 4 plus 1. Okay, it's negative 3. Now, if x is 1, we have negative in a bracket 1 minus 2 is negative 1. When squared and added 1, we have 0. If x is 2, it's even easier to calculate because 2 minus 2 is 0. So this part is 0 plus 1. Overall, we have the value 1. If x is 3, we have negative 3 minus 2 is like 1 squared, and then plus 1. So altogether, we have negative 1 plus 1, that's 0. Oh, we see the symmetry here. That's good, promising. If x is 4, we have negative 4 minus 2 is 2 squared, and then plus 1. So we have negative 4 plus 1, that's negative 3, as expected. Okay, so this point will be our vertex, and we may start graphing from it. 2, 1, that's this point. Here it's 2, here it's 1, and then 1, 0, so it's here, and 3, 0, over there. 0, negative 3, it's here, and 4, negative 3, over there. See, the same idea. If we start with the vertex, we go 1 across both ways and 1 down. Why down? Because of this minus. So that went down. And then 2 across both ways and 4 down. Let's join those points. Here we go. How can we obtain this graph from the graph of the basic parabola? Well, recall again the graph of x squared. It goes like this. So to be closer to our graph, first we should flip the graph of x squared over the x-axis to get the graph of negative x squared. And then to obtain our final graph, we need to move the vertex 0, 0 and consequently the whole graph of negative x squared by the vector 2, 1. That means we're going 2 steps horizontally and 1 step vertically. Here's the movement. Okay. So overall, what can we say about the graph of our function? The shape is of the basic parabola. However, this parabola is flipped upside down, so it opens down. The domain, as for any other parabola, is all real numbers. Let's look at the range of this shape. Well, if we project the graph onto the y-axis, everything will be covered from minus infinity until 1. So the range is from minus infinity until 1, including the 1. And our vertex has coordinates 2, 1. You see the connection between the coordinates of the vertex and the numbers that we used to modify the function. The 2 is inside the bracket, the 1 is outside. That's how we can read the coordinates of the vertex directly from the formula without using table of values anymore. Okay, let's record this. Vertex is 2, 1. Axis of symmetry, that's the line that passes through the vertex, and it's a vertical line. So its equation is x equals 2, the first coordinate of the vertex. Notice that any quadratic function given in a standard form like this can be converted to the vertex form, like that, by completing the square procedure. So the graph of any parabola will really depend on the leading coefficient a and those numbers h and k that we add or subtract from the x and from the whole function. How does it depend? Well, let's list the properties of a graph of a quadratic function on the basis of the above examples. The graph of any quadratic function given in a vertex form like this has the following properties. First of all, the graph has a shape of a parabola, similar to the basic shape of x squared. Secondly, the graph of our function will open up if the leading coefficient is positive, and it will open down if the leading coefficient is negative. In this example, we had a leading coefficient negative, that's why the resulting graph has arms down. Next, the vertex can be read directly from the formula just by looking at numbers h and k. The only thing that I would like to point out is that in the formula we have a minus inside the bracket and plus outside the bracket. Both h and k can be positive or negative, but keep in mind that the formula accommodates for this change in signs by using the minus inside the bracket. Let's see example again. The vertex has coordinates 2, not negative 2, 2 and 1. Therefore, we take the opposite number to whatever we see inside the bracket and exactly the same number that we see outside of the bracket. The following property is the axis of symmetry. Axis of symmetry of any parabola is the vertical line passing through the vertex. Therefore, its equation is x equals to the first coordinate of the vertex, x equals h. Another property, the domain of any parabola is all real numbers. And the following property refers to the range of a parabola. Well, the range of parabola will be read differently if a is positive. That means if our parabola has arms up, because in this case range starts from the y-coordinate of the vertex, which is k, and then goes towards infinity. So our range is from k to infinity. However, if the coefficient a, the leading coefficient, is negative, the parabola takes the upside down shape. So the range will be from minus infinity until the y-coordinate of the vertex, which is k again. So it's from minus infinity until k, like this. Therefore, we record the range from minus infinity till k with k. K is always taken because that's the vertex it is assumed by the function. Finally, we can talk about minimum or maximum value. So in the first case, if the leading coefficient is positive, we have this arms up situation. As we see, this k becomes the lowest possible value. So that's a minimum value that the function will assume. However, if the leading coefficient a is negative, the parabola has arms down and the value k is the highest possible. So this represents the maximum value of our parabola. Let's keep those properties in mind, as we are going to use them in the next video to graph more efficiently without referring to a table of values anymore.